Okay, Phononic, you are positioning thermal management as a serious limiting factor for AI performance. So, just how close are today's hyperscale data centers to hitting that thermal ceiling, and what does that actually mean in practical terms for operators? What are the, what's the impact of that?
For several of the workloads now, we're not just approaching the thermal ceiling. I think we're already there. Take training as a workload that would be specifically in mind for me there. We see the next shift as precision. Rather than overcooling for a few hotspots, it makes a lot more sense to directly cool those hotspots and let the bulk cooling kind of run at a lower sustained level as well.
Okay, and I believe in terms of the technology solution you're offering, you're citing, I think it's 0.15 potential PUE savings and three times RI. And what you're doing is GPU, high bandwidth memory cooling solution. So to your point there, I guess very targeted cooling. Just yeah, tell us a bit more obviously about the solution and I guess particular how therefore where those gains are coming from and how quickly the operators can realize them.
What's different than standard cooling is we can respond in milliseconds. And so that gives us about a 600 times control gap versus bulk cooling. And what that allows us to do is dial in those various things in a software defined manner. So the 0.15 PUE actually comes because we can run the technical water 15 degrees C warmer, 10 to 15 degrees C warmer than you could do otherwise. That gives you the PUE savings right there. We're already seeing on our next generation parts about a 14% overall power savings at the data center level by switching to our solutions just from running the technical water at 50 degrees C. Then also, when we do that, we can set the temperature that the device runs at to stay below all of the throttling things that happen. So we call this margin compression. Memory's refreshing multiple times, then you're starting to slow clocks, and eventually you're in a full throttle. That's lost performance that people don't know they have. And we can unlock all that by never actually running into those thermal excursions at all. So that unlocks a lot of performance, and so you actually can fully utilize the asset that you paid for. By running that cooler as well, you also get another thing where you can make the device last up to 5.5 times longer because your Arrhenius effect and thermal cycling are happening to you. You're keeping those temperatures constant. So we actually see our solution, especially for HBMs, as have your cake and eat it too. And now we're starting to proliferate that to co-packaged optics and other parts of the data center. Eventually, our vision is anywhere there's a fan or a hotspot, you could replace it with a thermal electric with this millisecond response time to give you precise control. And that's especially important as racks densify.
Yeah, so I mean, I was going to ask that, and you potentially answered most of the question, but I'll ask anyway. Industries rapidly moving towards the high density workloads and therefore the rack power required. So your approach in terms of how it differs, is it just I say just, I mean it's important, but the targeting of the liquid or of your cooling as opposed to traditional liquid or air cooling, which tends to sort of blast, most as you say, whether it's the whole data center or the whole rack, whatever. Just what do you do differently to handle those escalating thermal loads, I suppose is the question.
Yeah, so our thermal electrics allow you to place exactly on each hotspot. That could be an HBM memory. It might be actually your voltage regulator. It could be a lot of different parts within the rack. And then let the bulk cooling do what it's great at is getting all of that heat out of the rack and let us take care of making sure all the temperature irregularities are controlled and that bulk cooling can run most optimally for itself. So we see it as very complementary with bulk cooling for our solution. But yeah, anywhere there's a hotspot, we can go in and we can do it. And with that software control, we're only adding power from our solution when you need it to remove the cooling. Otherwise, we can turn it off.
Okay, and I know that the Gen 2 GPU HBM cooling solution delivers up to 75%, I think it is, higher heat dissipation. So just translate into real world impact on AI workloads in terms of sustained performance, avoiding thermal. I know thermal throttling is an issue. Yeah, just what is the difference users will see?
The the results that we've just gotten back in the last week are absolutely astonishing to me. I've never seen anything like it in my 30 years doing this. Uh, we talked about those three variables of PUE, performance unlock, and device life. With this newest part for HBM4, we're actually seeing that you can have all three of those simultaneous. You don't actually have to make a trade-off. And that is a massive impact on ROI for a data center.
And more generally, you've introduced the concept of a thermal fabric. So just explain to me how data center operators should think about this compared to whether it's DSIM or workload orchestration tools. Are you replacing those, or is it an additional control there? Just tell us where the idea behind it.
Yeah, we stick to our swim lane on this one. We see those as a very complementary as well, just like bulk cooling. You could kind of think of us as a layer in the middle between the two. On the orchestration side, it's currently void of any thermal signaling. And so you're placing workloads without actually knowing if thermally you can do that. So this becomes the new fabrics. We have compute network storage. Now you can add a thermal fabric and get a lot more precision and a lot more determinism in how you're scheduling your workload. On the DSIM side, we talked about the 600x lag. It takes about 4 to 6 minutes for the loops to react. We can react in milliseconds, so you actually can completely avoid thermal excursions, and you're not constantly over provisioning the water temperature. And so this signaling layer to each of those is incredibly valuable, we think.
And you mentioned co-packaged optics earlier, which is I won't say it's a pet subject of mine, but it's a fascinating topic. It's an emerging architecture. So what role do you think your cooling can play in accelerating its adoption? And are there any particular challenges you see as remaining when it comes to sort of scaling up the technology for production environments?
I think there's a couple different issues with co-packaged optics that are emerging. The first one is, how do you keep the laser stable? And that's what our thermoelectrics do. The laser actually sits on top of our thermoelectric, and that millisecond response can keep it stable. We're already doing that all the way up from 400 gig to 1.6T, and even have 3.2 designs underway. That's important, but what also happens is now when you bring it next to an ASIC, you get parasitics from that. And so it's even more important that you keep the laser very precise, because that extra heat coming from there. And then you take that ASIC and that whole device and you pull it closer to the GPU, and you start getting the GPU parasitics as well. And so we think our approach to targeting the hot spots and cooling them, if you need it and you can get the laser, great. Why spend any more money? But we can also start to look at what the ASIC's needing for cooling, cool there. And then we already talked about the HBM and even the GPU die itself. What also comes out of that, though, is we can see if you're having issues with the laser and give you a response signal up. So we can tell it's taking more power over time to keep the same temperature of the laser. And that starts to become a predictive failure mechanism that we can see in the device. And I think everyone's fear about co-packaged optics are, how do I know when it's going to fail? Can I predict that so that I can actually be smarter with my orchestration and not have a downlink?
No, that makes sense. And I think this one you did answer. But you are working, I think, with most of, if not all, the major hyperscalers. And I was going to ask, customers prioritizing energy efficiency, performance, hardware longevity, because normally there are the trade-offs. But I think you just told me the results are suggesting that there is no longer they need to worry about trade-offs, because they can, improve all of those things equally well, or at least, significantly. Is that right?
Yes, and
Mhm.
this is a bit of a choose your own adventure that we found,
Right.
depending on who you talk to. Some people are very aggressive on performance, and so we could actually make it. In my previous days at Intel, we used to unlock parts for gamers, as an example. It would be possible for GPU vendors to create unlocked parts that could run even higher, and so you could flex in that direction for even more performance. If you were more interested in making your amortization table meet your actual device life, you could actually run it even colder still. Or what I think probably will also happen is, hey, it's great that we can run the water temperature 10 degrees warmer. What about 15 or 20? What would that look like? And can we save even more energy, repurpose that energy for even more compute?
And maybe just in finishing, I guess there are various sort of constraints or challenges in and around the data center, but thermal physics would seem to be a key one. So, with that in mind, what do you think the next generation of AI data center design might look like, or is already looking like, I suppose? And in terms of that, to what extent will the evolution be driven by the cooling innovation? Versus advances in the silicon, which was almost daily we seem to find somebody's doing something incredible with the latest iteration of their chips. But yeah, just your thoughts, I suppose.
Yeah, it's funny. For most of my career, it was how do we make the compute better? And then networking and storage would have to react
Mm.
with that as well. Bulk cooling would just do more of it. And it was kind of a great cycle for decades. Now we're into the place where both power and cooling become primary design constraints. And as densification happens, it only gets worse. And so I think the industry shift is really around how do you think of thermal as a constraint and how do you pair this hotspot cooling with that constraint? And I'll give you an example of some of the discussions we're having. On a GPU die, HBM is a problem, and people are already talking about how they can unlock that. But there are other spots on there too, whether it's a matrix multiply, a cache, or other places that are getting hot. We could see a world where you're actually just putting thermal electrics on each of those hot spots and then running them when you need to cool all of that as well. And I think that mindset shift is pretty significant for people, and is a way that people are going to actually gain the next layer of differentiation and performance.
And just your thoughts. I mean, I know another potential solution. I'm not saying there isn't need for cooling at a the component level, but the idea of dropping the whole sort of IT hardware system in a bath of whatever liquid, immersion cooling. Just Is that got a role to play, do you think, or do you think this very targeted, very efficient cooling that you've developed and others is the way to go, or can you see the attractions of just dropping everything into one bath of liquid?
Yeah, I think to me, there's kind of two things. We could extend the current generation with our solution of bulk cooling. And then as the next one comes along, you still have hotspots. And so you still need some kind of targeted cooling as well. So whether it's microfluidics or immersion or any of these things, we see those as still complementary to what we're doing from our perspective. And you can't get the millisecond level of response time out of immersion,
Of
but you
course, yeah.
can get rid of a lot more heat, which is great. That only makes our solution better, and you have to run it uh, less power, which just brings the whole solution and makes it more efficient.
That's great. I mean, it's been brilliant to chat, and thanks, Ryan, for sharing so many great insights into what's going on. I've been involved in data centers for 20 odd years, and as you say, you said you'd never had the results like that. I've never seen a time like it in terms of what's going on. So it's been fascinating to chat, and thanks for sharing so many great insights. Appreciate your
Of
time.
course. Yeah, appreciate the time.